what I'm going to talk about is waves, and we use the thing lasers, tsunamis, and beyond to get you here, but what kind of wave is this? Sound wave, but what kind of special wave is that? Shock wave, right? So when you hear a sonic boom, it's sort of like that. What other kind of waves are in the room right now? Light waves, they're coming at you. With any other things you can think of right offhand? Radio waves, they're coming through the roof when you turn on your radio. Does everyone have satellite TV? Right? If you have satellite TV, you have waves coming in from your satellites. What other kind of waves? Anyone here ever have to go to the hospital because they broke their arm or anything? Leg, anything? Anyone here ever have a X-rays? That's a wave. Those are electromagnetic waves. What kind of waves do you get sunburn from? UV waves. When you're out in the boat somewhere bobbing up and down or swimming in the ocean, you have water waves. I thought you were the smart kids. Okay. Water waves. What's earthquakes have? Seismic waves, right? So there's waves sort of all around you all of the time. And we're going to be talking about those today. Now, we have 1 hour to talk about it. One of the things we also have is the issue of when you make up popcorn or something. What do we have here? Microwaves, right? So let's see what they have.
Here we go.
Yeah, it's ready. Okay. It's a little hot, but I'm leaving. Okay, so let's talk about our first wave. Here we go. Let's hear from the band. Hey, that's great. Hey, I want to play that picture one time more. I want you to watch something about this wave, because I want you to think about that. That surfer's moving along at a pretty good rate, right? But where are they on the wave? Let's watch it. Is the surfer moving on the wave? It's pretty interesting, right? That surfer is just falling downhill while not moving with respect to the wave. We'll learn more about that later. Okay, that's a pretty interesting point. Well, there's all kinds of waves. Here's a small wave. This is someone throwing a pebble into a pond, right? And let's play that again so you can just check it out. How big are those waves? They're sort of like this, right? The little concentric circles coming out. Now that's another kind of wave. There's also some pretty big waves. Does everyone remember the big earthquake in Sumatra? Right? Does everyone know where that is? Well, let me just point to it, see if I can find it myself. Right here. Ooh. Right here we had a pretty big interesting event here. Let's watch what that looked like as a wave. This is a computer simulation of that wave. Here's a wave heading towards Africa, around Australia, Antarctica, bouncing off. It's just gone past Africa. It's hit into South America, into the Pacific, up to North America. This happened on December 26th, about a year ago, right? A year and a half ago. This is a pretty interesting event. By the way, this wave, as it traveled around, looked very similar to that little pebble wave, right? And this is, of course, it has slightly different consequences. Now this is a simulation, but you can see you could get a wave not an inch high, but you could get a wave 100 feet high when it comes on shore. So these waves are also moving very fast, 500 miles an hour. So they move the same speed as a jet aircraft when you're flying over the ocean. So that's a tsunami, right? That's a really big wave. We can study those waves in real life, and Rick Sawicki is going to come out and do it. Can we have this stage lights? So we're going to have a wave tank demo and show you how to do this.
Hello. Are you having fun so far? Okay. So now let's have a little bit more fun, but this time with the wave tank behind me and create a tsunami, which would be a pretty cool thing. So in order to create a tsunami, I think you need two things. And who could tell me what the first thing is? Water. You need water. Okay, so let's come back here and take a look at this water. So we have water here in this wave tank. And a wave tank is something that is used by many engineers and scientists to study the interesting properties of waves. Have any of you had the opportunity to play in a wave tank? Any hands? A couple of hands. How many of you has seen something maybe in your science class on a movie perhaps about waves? Okay, they're very, very useful instruments for studying the different properties of waves, and I'd like to talk about a couple of those. Now, to create a tsunami, you need one other thing besides water. Can anybody guess what that might be? A wave? No, we're going to create a wave. And how do you create the wave? A force. Did someone say force? Okay, that's pretty close. What you need is a disturbance. Ed showed the picture of a rock being thrown in a pond. That was a disturbance that created a wave. Okay? In the big tsunami in the Indian earthquake, the disturbance in that particular case was an earthquake. And what did the earthquake do? The earthquake lifted up land underneath the ocean in one part of it, but didn't lift it up in another part. And so this lifted up the water above nearby water. And that was the disturbance that caused the tsunami. And so what I would like to try to do in this experiment is to duplicate that condition. Okay, so I have a piece of plexiglass here. So what I'm going to do here is put this piece of plexiglass in the middle of the tank, and I'm going to move it to the side. And I'm going to caulk it in the tank so that the water can't leak around its edges. When I move it to the side, this water will rise, and you will see the water over here lower.
So we're just pushing the water from one place to another.
There we go. Okay, so I've created this wave. It sloshes back and forth. And that's what a wave is. It's the transport of energy from one location to another. There are small oscillations of the water molecules in this tank that are moving. They're primarily moving in the vertical direction.
Wait.
What do you mean? Wait.
So you're saying that energy is moving, but matter is not, mass is not?
Yeah, that's exactly what I'm saying.
Well, the only thing that I've ever seen energy moving is like when you throw a ball. So I put energy into it, and it goes across the room. So
no, that's not the way that waves work, and I'm sure that I'm right. In fact, I'm so sure I'm willing to make a bet.
How much?
If I'm right, I get to take the day off on Monday. And if you're right, you can take the day off.
Well, I'm taking the day off, so there's no problem.
Okay, so let's do a little experiment, and what I'd like to do is put some matter into the tank. And I'm going to put this in, which is Leo the lobster. It's a little float. And I'm going to put this in the middle of the tank. It represents some mass. And so now the question is, what will happen to Leo if I create a wave? Is he going to slosh back and forth from one end of the tank to the other, or is he going to bob up and down like a boat in the middle? What do we think?
Up and down.
All right. So let me create a wave here. I'm going to make it a little bit smaller one. It's getting a little wet up here. So I'm going to go like this and then lift up. So you see the wave moving back and forth, and he's moving, oscillating back and forth a little bit, but up and down. If you were able to look at the molecules, very small particles that were in the tank, they would actually be making elliptical patterns. And as a wave approaches the shore, those elliptical patterns become more and more vertical, resulting in these huge waves that you sometimes see when you go to the
Okay,
beach.
so Rick, what you're saying is that even though energy is going back and forth, the molecules of the water are pretty much staying where they are.
Right.
Okay, well let's explore that.
Well, actually, do I have the day off on Monday or not? I think I want. Let's
Rick,
let them decide. Do I get the day off?
It was a trick, Rick. I don't know. So anyway, we did the ball toss. So let's talk about the properties of waves. Now that we know something very important about them, and something you should always remember, waves can transport energy without transporting matter. Standing waves are very interesting. So what are the properties of waves? Okay, so 1 second. So let's just do something. Let's just try to make a half wave standing wave. Okay, does everyone see that? What's the difference between a traveling wave and a standing wave? Right, nothing is moving this way, just moving up and down. So if I stand here, it's just, but but if I stand here, nothing is happening. Now, if we go a little bit faster, what happens? Let's just try to make a sine wave.
Okay.
Has anyone taken trigonometry yet? That's a sine wave. When you take trigonometry, that's a sine wave, right? Okay, so let's talk about some things. When a wave is loud, or high frequency, we have some things. So let's play a high frequency thing. Whoa. Okay, let's have a low frequency one. Okay, high frequency. So that, we can look at it over on the screen over there, right? High frequency, low frequency, right? So that is the wavelength. Now let's make a loud one and a quiet one. You can play an A or anything. Now play it loud. That's amplitude. So that's the amplitude. Let's do bass a little loud and quietly. Where's Diane Hardy? Come on up, Diane. Okay, so you get that idea, right? Now, let's see if we can do this, and we're going to have you help. Diane actually happens to be a pretty good singer. Why don't you sing a high note? Whoa. Let me try. Ho, 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 ho. Okay, Diane, why don't you help them sing high notes? Everyone, let's try to get a high note so you understand high frequency. Ready? Go. Okay, so you know what a high frequency is, right? Now let's just try to do a low frequency. Everyone? You're experts. Thank you, Diane. Okay. Okay, so we now know properties of waves. Now, what kind of waves exist? Okay, so let's talk about when Rick and Craig were showing that wave, what kind of wave was that? That was a transverse wave. What does a transverse wave mean? That the energy is traveling in one direction, but the oscillations or disturbance are perpendicular to it. So when you're at the beach, that's what you're generally seeing, right? Energy is going that way, but the waves are popping you up and down that way. That's not the only kind of wave there is. There's another important kind of wave called a compression wave, right? So when you have a slinky and you hit it on its end, and when you have your slinky, the end of this, you just do this. So there's a compression wave, right? So I want that row that practice compression waves. I think it's the 4th row or something. The 5th row, come on up here. Let's go. Let's get up right here. Let's give them a round of applause. Okay, so come around here. Now this is going to prove that we can transfer energy from one place to another without moving matter. Now, do these people look to you like molecules in the air? Yeah, they look that way to me too. Well, some of these are oxygen and some of them are nitrogen. And some of them are slow and some of them are fast. Okay. Okay, so we're going to have them packed together, show that we need someone over here, Damien, to prevent them from falling over, right? Okay, so we want to pack up together, right? Okay, so what I'm going to do is start this sound wave. This is a compression wave through the system. Now you watch it roll. Just ready? So I'm going to hit. Let's try one more. Now, did energy move? Did they move? So there you have a compression wave. Why don't we pretend, does sound travel in a vacuum? No? Why not? Okay, well let's do some tests. Let's pretend we're going up in altitude. So we're up on, not on Mount Everest, let's go up on somewhere in the Sierras. So we're going to take some air out, so spread yourselves apart. Okay? So the molecules are getting further apart. That's what a vacuum is, right? So let's just try this experiment now. Do you think the wave is going to go faster or slower? Okay, well, let's see. This is really what happens. So I'm going to give Greg that little push and see, we'll watch what happens. Don't knock each other over. See how that wave is going? Whoa! Okay, now I want to do another test to see what happens. So it goes slower, and actually it's not as much amplitude. Here's another one. Every other person, starting right here, step forward 1. You. This is like we're getting to a vacuum now. Okay, let's try to propagate a wave now. They really can't, right? So when you have a vacuum, and no sound can transmit through it. So whenever you see that, thank you very much. Let's hear it for the bumper wave crowd. Wave, and that's the human wave. Let's now do a human transverse wave. Do we have ready? So we're going to ask the first 3 rows to do this. Okay, let's get. Are you guys ready? Okay, so what we're doing is we're going to tie you together by just holding these safety things. Everyone just sit down. Don't anyone get up. Just take one of them. Can you hear me now? Just one, right? Just then we'll do the second one. Okay, then we'll do the third one. Third row. Okay, does we have the second row have one? The third row. Now. Okay, now actually tighten them up. Everyone, I want you to put your hands out like this. Okay, so this is a transverse wave. Now the way a transverse wave works is that you go up like this and down, right? I don't mean you go up and down. I just want you to do up, down, right? Whoa, 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 whoa. I didn't say now. And you don't go up and down until you feel the pressure coming up. So 1, 2, 3. Okay, so we can transfer energy all the way through there. And in fact, if we had a long enough string, we could send it all the way through the room. Okay, now let's do one of these another experiments. Let's loosen up so we have some slack between you. Put a little bit slack between you so you're not really tightened. Okay, is the wave going to go faster or slower? Why do you think? Because it takes a little bit of time for the time one person goes up till that energy starts moving across. Let's try it right now. You all ready? 1, 2, 3. It's kind of cool. You see that sine wave propagating through? Well, sometimes it is. Okay, thanks a lot. So how other ways can we transfer energy through the air? Is this ready to rock and roll? Yep. Okay, so most times when you play a drum, what do? Bang it, right? You think we can play this drum without touching it? How do you think we would do it? Say it again? Sound wave. So let's put a sound wave on it. Okay, so here we are. I don't hear it. We're playing it. Play it. Okay, so do you think it would work for any frequency or any sound we put on this drum? Well, let's try it. We'll change the sound frequency. Stop, huh? Okay, put it back up to the right frequency. Okay, I want you to think about that because we're going to come back to that. I just want you to know it is 160 times a second that sound was coming out. It plays that drum. If you go at some other frequency, it will not. 160 times a second is sort of a higher note, and that's sort of the resonant frequency of that drum. It's sort of an important thing that we'll come back to. Where else do we have drums, snare drums in our lives? What? The band room, that's one place there. How many people do you think are in this room right now? I think downstairs holds like around 400 people. So I say there's 300 people. How many snare-like drums do we have in this room? 600 or so. Where are they? Right, our ears. You know, our ears are drums. If you look inside your ear, there's an eardrum, right? And it acts just like that snare drum. When sound comes on it, it vibrates. And an eardrum is kind of amazing because behind your eardrum you have all these little resonant pipes that pick up different frequencies that your brain interprets as sound. So that is what's going on in your ear. So we have that kind of exact same thing as a snare drum in your ear, except it's a lot fancier. I want to do another thing. Rick, you ready to rock and roll? Okay, how many people think that they're all hearing the same sound no matter where they are in the room? Okay, so we're going to do an experiment. I actually think you are hearing pretty much the same sound, but if we put a pure tone in the room, let's see what happens. Now, Rick's got up here, we're sending out a tone of, I think, around 600 hertz? 606 hertz, or 606 times a second. And what he's doing is checking the room where that sound is. So he has a microphone right here, and he's going to move around and try to find places where there's no sound.
It actually changes in amplitude, right? Now it's pretty big. I'm going to walk back. Whoa, what's this right here? Right. See if I can find it.
Okay, let's do a test. Cover one of your ears.
Okay.
Now, do some people hear it and some people don't? Does anyone sort of hear it very quietly and some people hear it very loudly? If you move your head, I can feel it. If you move it especially this way. So what he's doing is he walks back and forth. He's finding places in the room where the sound is going up and down. So this is just sort of like a big snare drum. So let's go on. Okay, thank you, Rick. So here's another kind of wave. Now this is a little bit Hollywood, but nevertheless, what kind of wave is this? Seismic wave. Does anyone think this is like an over-dramatization? If you were alive in 1979 in the Bay Area, how many were? 1989, sorry. 89. Well, all of us elderly statesmen were, but a lot of you weren't. We had a big earthquake around here, and this actually happened. This was Oakland. This used to be the old 880. And this actually, that earthquake, the kind of ground motion we saw, right in our backyards, knocked down that freeway. It's pretty interesting. Here's another amazing picture. How would you like to ride on that railroad? There's two things you see about this picture which I think are very interesting. First of all, you see displacements that are side to side, right? Look at that sine wave. But a railroad track is tried to be perfectly flat, right? In a railroad bed, that's what they do. Look at that rolling as it goes through. That was a seismic wave rolling through there, and after it went by, that's how the land settled in. So you can see an earthquake can really distort our Earth tremendously and cause great damage. Now, how does an earthquake work? Well, let's look at it. This is a little cartoon. They're generally near the surface of the Earth, right? Let's just stop this. What's happening? What are those waves going through the center of the Earth? What kind of waves do you think they are? Yeah, they're seismic waves. Are they transverse waves or compressive waves? They're compressive waves. What about the ones that are going on the surface of the Earth? Well, I'll just move this forward a little bit. Let's watch that. Watch these little people. What kind of waves are those? They're transverse waves. So what you have when you have earthquakes, you have transverse and compressive waves or longitudinal waves doing this. And if we follow this earthquake to the end, you can see that. They call, I think, the S&P waves. Let's go over this, Rick. The primary waves are, I think, the compressive waves, and the secondary waves are on the surface of the transverse waves generally. When you have an earthquake and it hits the Earth, it's right? And hear how that's ringing? That's exactly what's happening to the Earth. The Earth is like being hit like a hammer. And the way we show that, like we had a wave tank, we made a model of the Earth, and that's how it actually works. Right? So that's a balloon filled with water. Right? Let's play it again. That's an earthquake hitting it, and you watch those waves traveling through the Earth and on the surface. Let's just do it again. Right? And what happens is the whole Earth rings. And if you look at the Earth, it looks like this. Now, of course, it doesn't look that big. I got to tell you an amazing story. In around 1300, an asteroid hit the moon. You know, a big asteroid hit the moon. And some medieval monks in Europe and in China actually recorded it. And what they recorded is a big dust cloud all of a sudden covering the moon. And what had happened is a very large asteroid had hit it. Now, about 600 years, 700 years later, you know, our Apollo astronauts went to the moon and they put mirrors. When they left, believe it or not, they left some mirrors on the moon. People have been shining lasers on the Earth, from the Earth on those mirrors for a long time. And studying where the moon is and certain things about it. Does it have moonquakes and stuff? Let's move on to resonances. One of the first resonances I want to talk about, whoop, this is not my slinky. What? Oh yeah. Does everyone know what a resonance is? I don't think so, right? Okay, so let me just use this slinky. Let me just bring it back. If I just drop it, what frequency does it go at? It has what kind of frequency? It's called a natural frequency. It just goes on its own, you know, just like this, right? Now, if I put my hand up and down exactly that frequency, you can see it just goes wild. So that means I'm resonant or at the same frequency as this slinky wants to oscillate at. Does everyone get that idea? Okay, now what if I do something like, instead of going down, up and down at the frequency it wants to go at, let me just do it, if I go real fast. Even though it looks like I'm moving my hand more, does the slinky respond? No, hardly at all. What if I go real slow, much slower than the frequency of the resonance? Slinky goes up and down, but it's not responding. But if I go just right at that frequency, just have the littlest motion, and I can pump energy into it. That's called resonance. And that's what we were doing with that drum over there also. When we tuned it up to 160 hertz, that is where that drum wants to ring. Now, there's a lot of resonances in your life all the time. You know, bells are resonant, many things are resonant, and they have very important effects. Let's look at that balloon again. This is a three-dimensional slinky, right? If we just let it roll, you can see it popping up and down about 1 time a second. That's 1 hertz, right? Let's watch it again. So that's resonance there. That means if I pull that up and down at 1 time a second, it would really go wild. In fact, the balloon would break from the stress. Here's another one we have. You saw that Ella Fitzgerald broke that glass. You know, have any of you ever done this trick? So what am I doing here? Does anyone know? Okay, what's happening is I'm exciting the resonance of this cup. And if I look at that, what's really happening, and I can look at this movie, what's going on is that cup is actually ringing like a bell because of what I'm doing with my fingers. This is really being driven very hard, almost to its breaking point. But that's what resonance is. This is a slow motion version of that. So when you hear that, ooh, and if you put more water in it, of course, it'll change its tone. If you put less water in it, it'll change its tone too. So sometimes you see people who can play music on those things because they have different resonant frequencies. Now, if you really push this really hard, what happens? Breaks. This is what Ella Fitzgerald did, right? And that means you just pushed it so hard that it didn't have strength enough to stay together, and it broke. It's sort of like hitting it with a hammer and just letting it go. Now, resonances can happen not on small scales, they can also happen on really big scales. Okay, so let's look at this. This is a famous bridge, Tacoma Narrows Bridge in Washington. You know, as you go through school, you'll see this many times in your life. This was a great architectural achievement. It was the first time people made a bridge with this very thin roadbed. It was sort of not a very great engineering achievement. As we can see, what's happening to this bridge as it goes? Look at that mode. It's resonant. Now it's twisting. We'll come back to it in a second. Now, you notice something that's going to really bother you any moment. Look at the way those cables are. Is there something on this bridge that doesn't belong there? There's a car and a person. Now, what was he thinking? I mean, he didn't just drive on there and it was a steady roadbed and he said, well. Anyway, he decided halfway on there he'd better get back. And he did make it back. But look at how those cables are now flexing also, right? Finally, the cables break and it just snaps. Let's just look at this thing again. Right? The first thing I want to show is you can see that it's flying up. That's that half a mode that Rick showed and Rick and Craig showed with the slinky, right? Now, well, I can show you something right here. First, it was doing this, right? Just going up and down. And what was happening to the cables that were holding it? They were pushed up and then dropped back. So they were being under great tension. Then it started doing this, another mode, right? It was twisting. That's another natural mode, another resonance. It started twisting back and forth like this. So then it had combinations. It was going up and down and twisting. Finally, those cables couldn't take it and they broke. So let's watch it now that you're expert at it. Whoa. Oh, here it is. Watch it now with your eyes, right? So we're going to do it. Here are the twisting modes coming in, right? So you can see the combinations of modes. Now look at the lamps. It gives you a feeling of how far it was going. Look at those cables, what they're doing. They're starting to resonate on their own. Look at this knucklehead. He's starting to resonate. He's trying to figure out how he got here. Why is he walking down the center? What's the answer? He's trying to be at the center of the standing waves, right? So when that thing is twisting and going like this, the center is the easiest place for him to walk. So even though he realized he shouldn't be on the sidewalk, because that's the worst place to be, right? So he figured that out real quick. So you can see that that road was the most stable there. Finally, it rips apart. That's resonance. You know, and so you can have good, you can make good of it, like when you're playing musical instruments, or when Diane was singing that beautiful note where she was resonating her vocal cords with her mouth to get that perfect note. Or you could have this kind of destructive thing too. Okay, let's watch lightning. Does everyone know what causes lightning? Okay, so you have electrical discharge and it goes through the air, heats up the air very hot. When it's very hot, it blows out the air and makes a vacuum, and then the vacuum sucks the cold air back into it, right? And then bam, when it comes together. Okay? So let's watch this now, and then tell me why it takes so long to hear the thunder after you see the lightning. 1 Mississippi, 2 Mississippi. It's around 2.5 seconds. How fast does sound travel in air? Say it again? 700 miles? Yeah, it's around 700 miles an hour. That's Mach 1. You know, so if you think about it, it goes about a second it takes to go 5 seconds it takes to go 5 miles. So if you go faster than the speed of sound, Mach 1, you're going around 1 mile every 5 seconds, right? So it's about 12 times faster than you travel in your car when you're on the highway. So anyway, so we could tell this was around 2 or 3 seconds apart, so it's about a half mile away. If you ever are near lightning, which most of us aren't because we live here, but so you hardly ever get lightning, if you see the lightning then hear it immediately, that means you're way too close, you're in a bad place, and you should get out of that place. You know, lightning is very dangerous. Okay, but that's where now that we've talked about lightning, let's talk about light. I think light is the coolest kind of wave. That's what I think about all the time. What kind of light waves do we see here? Does anyone can tell me some? What's in the building? What kind of light is that? In the building we have, I'll be fair. Those are fluorescent lights, right? What kind of light do we have? We can see those red lights down there. Those are car lights. Those are incandescent lights. Those are just hot wires. What's up in the sky, that dot, well, that big disk up in the sky? That's moonlight. That's actually light coming from the sun, reflecting off the earth, going up to the moon and back to us. People think moonlight comes from the sun to the earth, to sun to the moon to the earth. It really goes from the sun to the earth to the moon to the earth. But anyway, we won't. And then we have the most interesting light that we'll talk about. What's that straight beam? That's a laser light, right? This was at the lab a long time ago. Light is a transverse wave. Remember when we were having that slinky going up and down? It was in one plane, right? It was going up and down. That's polarized light. And you can polarize it vertically, like you can see on your right, or horizontally, like you can see on your left. Or, believe it or not, you can have circularly polarized light. Light can just be like a big spiral going through space. And light is very interesting because it covers a huge spectrum. When we talk about the light that we see, which is visible light, it's only a very small amount of the light that we have. Are we going to do an ultraviolet light demonstration? So, what you see we see, visible light. But as you can also see here, the electromagnetic spectrum includes radio frequencies, microwaves, infrared, ultraviolet, X-rays, and gamma rays. It includes it all. And it is, if you measured all the energy in the universe, electromagnetic radiation is the predominant amount there is. Okay, so first of all, you know about ultraviolet light, right? That's the stuff you get sunburns from. Right, and if we use some dye, can you guys see that? That's a dye that absorbs ultraviolet light, and says waves, right, and absorbs it and then fluoresces in the visible, so we can see things better using ultraviolet light. Light travels in a vacuum. Does sound travel in a vacuum? No, but light does. How do we know that light travels in a vacuum? And what? Yeah, we can see the stars, we can see the sun. Have we ever heard the sun? When you go out on a sunny day, do you go, oh, the sun sounds nice today? I don't think so, because there's about 93 million miles of vacuum between you and the sun. At the same time, electromagnetic radiation, as amazing as it is to me still, after 40 years of thinking about it, goes through nothing. So how can you imagine that happens? This is what Einstein actually got famous for. So this is really, when we talk about special relativity, this is really what he was thinking about. How does light go through nothing? And if any of you ever get the answer and can explain it to me, you can come and give this class. Okay, so that's what's going on. I also want to show you this X-ray picture of the sun. The electromagnetic radiation comes in a lot of flavors. Here is another one. Here's how the sun looks through an X-ray camera from a satellite that's circling the sun that we put up. So here's a camera that's in orbit around the sun, not around the Earth. And you can see these solar storms and these flares popping out. And the reason we know they're X-rays is because we're looking with filters and cameras that only can see in the X-rays. That's a sort of a different, scarier picture of the sun. Okay, where does light come from? I'll go back to my bong, right? My gong. If I hit my gong, I know where it comes from, right? I'm hitting a mechanical device with a mechanical device. It's vibrating, we make sound. Light is a little bit better, right? Light comes from atoms or molecules. So this is a different scale. Now, when you guys think about atoms, when you're talking about them, right, you sort of think of these electrons in little orbits like a solar system around the nucleus. Is that right? Let's just do it again. So here we see the nucleus in the center, and we see the electrons going around in different orbits. And when an electron goes from one orbit to another, it puts out light. So we can see that, and there's some yellow photons coming out. What do you think it really looks like? Do you actually think in your mind's eyes, or do you think that's how it is? That's a trick question, If you say yes, I can say you're wrong. If you say you're wrong, I'll say come up and explain it to me, right? What really is going on, and this is when you study quantum mechanics, which I know, has anyone taken chemistry yet? Okay, so are you all quantum mechanics? This is what's really happening. If we have a quantum mechanical view, we have these blobs, these electron clouds. They don't even look like those orbits at all. And when you go from one type of orbital to the other, it goes from, like in this case, a 2p to a 1s, for those of you taking chemistry. This is what happens, and that's how we get light out. So I'll just do another one, just play it again. So instead of those nice orbitals like the solar system, this is really what it looks like. It's big clouds of electrons, even though it's only one electron, oscillating back and forth. Now what's great about this is, when light comes out of an atom, you get this spectrum, or you get these lines of color of light. You know, it goes from the UV, X-rays, it depends on what kind of element it is and how hot or whatever it is. And what's interesting about it, these are the fingerprints of that material. So, you know how we talk about the DNA of people, or when you hear about DNA in court cases, where you can have an exact fingerprint of what that person is, who their parents are, or whatever? You know, with these spectra, we have the quote-unquote DNA of the elements. So we can look anywhere in the universe and look at the color of the light that's coming out of it and tell what is there. So I can look, you know, over to the sun, or I can look through the galaxy, or I can look 10 billion years back to the beginning of time, and I can tell what's going on. It's an amazing capability. In fact, here's a picture of our Milky Way at 4 different colors. And the top one is how it looks in the visible, and the bottom one how it looks in the near infrared, and then we go to the infrared, and then to very long wavelengths in the radio frequency. So why, I think it's a very interesting question, why in the visible do we see that dark streak down the middle? Why in the infrared it looks very bright? Does anyone have an idea? Well, this is sort of a greenhouse effect. If you look through the galaxy, you know, the stars behind the dust in the plane of the galaxy are absorbing all that energy. So the visible light cannot get through. But when it absorbs that energy, what happens to it? It gets hot. So when it gets hot, it puts out infrared light. So when we look at it with an infrared camera, we can see it. So that's why you go from the top one where it looks black down the middle to the infrared ones which look bright down the middle. Okay, so that's the same thing. Okay, what's my favorite kind of light? Laser light. Light amplification by stimulated emission of radiation. If you were here last year, we talked about these big fancy words, but you know what, the thing that you have to know about laser light, it's coherent. And we're going to discuss what coherent means in 1 second. And we're going to do it by helping you work with us. How many people were here last year? Well, we'll do it again anyway. Okay, so first we're going to do just clap. I feel very lonely up here, and I'd like a round of applause for how well I'm doing right now. Okay. I really wanted more, but I'll take that for now. Now I want to do an experiment. Okay, so I'm going to tell you to start just clapping regularly, right? Okay, if you guys got to look at it, take this down. I don't want this. Okay, I want you to start clapping regularly. Wait. And then when I just do this, right, I just want you to clap together. And I'm not going to say how to clap together or what, but I want you to synchronize your clapping. Okay, let's just clap. Okay. You guys are so good. That's what laser light is, right? It goes from incoherent to coherent. Want to try it again? Okay, just do it again. Just clap. Okay. I want to do another coherence trick. I want you to all do this. I want you to just wave like this. Okay, now I want you to try to synchronize. Now you can put on the camera. If you're looking out there, which not all of you can see, you're doing a terrible job. Why is that? One thing a laser has is feedback, right? You know, a laser has feedback. So when you're clapping, you're getting feedback of all the sound in the room, right? So you know all about each other, right? So I'm going to ask you to turn this off again. So I'm going to give you some feedback, and I'm going to give you the funniest kind of feedback. I want you to look at this gentleman right here. And I know you can't see him, right? Yes. I know most of you can't see him, but I want you all to look here. Okay, so now start waving. Just look at him and synchronize. Wow. Isn't that amazing? In case you can't tell, you synchronize like bam, even though you all can't see him. Why is that? Because that wave propagated out. You know, information about everything that was going on here went to you. Whereas if you don't look at him and try it. See, you have no idea where any of the rest of you are. So that's coherent. So now that you know that, let's do some more tests of you. Is this a laser or a light bulb? Light bulb, right? They just randomly, they don't know about each other and couldn't care less. What is this? Yeah, they're in lockstep. So that's why lasers are so cool. Is that why this laser is a small spot across the room? Yeah, that's it. So that's why we love these little babies. If you had a flashlight, I don't think it would look that good no matter how. It's real bright. Okay, so let's go on that. So when was the first laser invented and how big was it? There it is. That's Ted Mayman. He was used aircraft. This was 1960. So that first laser was, look up here, was about this big, right? And it had a little curly Q flash lamp around it that powered it up. This was a major event in the history of our times, you know, the invention of the laser. But we're going to talk about a really big laser now. And this is a laser that's at the Livermore National Laboratory. I can just point it out. I mean, first of all, just to get you oriented, there's Hawaii, right? And there's San Francisco. There we are. And there's NIF, right? Right here. So that's a big laser. If we look down on it, we fly down on it, it's not the line of laser I'm holding in my hand, right? In fact, if you look at it, you could put 3 football fields on the roof, or you could put 2 soccer fields on the roof, right? So it's quite a big building. And what are we trying to do with that system? We're trying to build a sun on the Earth. So even though the sun is 1,000,000 times the volume of the Earth, we would like to find a way to put that on our Earth and be able to do experiments. And by the way, not just any sun, not just our sun, but any sun. We could do, there's hopes of doing neutron star type experiments, and the like. So what do? That's the size of the sun we want to make. So that's a real size eye. So it's not real big. But believe it or not, if you look at this, you can get a tremendous amount of energy out of this. So what we have here is this gold can that I just showed you. It's about a centimeter in size, and inside of it there's a hydrogen target. And that hydrogen target is little, it's just the size of a BB. And we have a capsule wall, which is made out of plastic, and then we have frozen gas in it. Frozen hydrogen gas, and what we do is we put laser light into it in a few billionths of a second, and we heat this up to X-ray light, so we're doing more waves, right? And these X-rays then hit the target, and they heat up that target really hot, really fast, and it starts blowing off, and now we have these compressive waves, shock waves going in, and it gets so hot that we can get thermonuclear burn. So let me just do that one more time for you. These are all the kind of waves we were talking about. So we have this gold can again. We have this BB-sized target in it. By the way, we can get more energy out of this than you can get out of a grenade. And we have essentially hydrogen gas, which is what you get from water. And we hit it with laser light in a few billionths of a second. I want to stop it for a second. Does anyone know how, and remember I told you light travels 500 million miles an hour? How far do you think light goes in a billionth of a second? Anyone have a guess? 1 foot, right? So a billionth of a second is not much time. So it goes 1 foot in a billionth of a second, okay? So here we have light, we're putting it in a few billionths of a second, right? And let's continue this. And this can is getting really, really hot. It's a super hot oven. In fact, it's an X-ray hot oven. The X-rays come and they hit this target. Now what happens? I'll stop it. The target is real hot. What happens when something gets real hot? Right? What happens is that it gets so hot that it starts falling apart and it blows off, right? And as it blows off, the word is ablate. It's a fancy word, but it means it just starts blowing off. What happens? Whose laws come into effect now? Newton's laws, right? Every action has an equal and opposite reaction. So as the walls come off, the ice on the inside that has to go in. Otherwise, it would start moving in some strange way. And so now we're compressing that center target. And at some point, right around here, you know how hot it is? It's 100 million degrees Kelvin, which is, just to make, I always say this, it's 180 million degrees Fahrenheit if you were to measure it that way. And you know how much pressure we have now? Right now we're standing here, we have what we call 1 atmosphere of pressure, right? So that's how much pressure we have on us. If you go to the bottom of the deepest part of the ocean, you have 1,000 times more pressure than we feel right now. And we'd be crushed to death, But if you went to the center of that target, you have 100 million times more pressure. So this is, about 100 times denser than lead at that point. And at this point, we now get to a situation where we get ignition, and we burn the nuclei up. So that's kind of cool. And the reason we want to do this, the way we do this is we have this big laser building, and if I take the targets off, we start off with a little tiny pulse of energy, and we send it through our amplifiers. This is, remember, 400 feet long. And then we send it towards the target chamber, and when we get right here, we just put it right on the target, that little tiny target. So this big giant building, that little tiny target, and bam, we get that energy out of it. The reason we want to do this is, of course, one of the reasons is, first, let's fire it. Let's see how this looks in real life. Okay, what kind of waves were those? Shock waves. Those are shock waves in the flash lamps that fire it up. And what other kind of waves did you see coming out of it? Light waves, right? That wasn't the laser light, but let's do it in slow motion so you can see it better. We'll do it 100 times slower. Does this sound like something? Sounds like thunder, right? So we're firing our laser regularly now. Even though it's not completely done, we're firing it regularly. And when we do this, we hope someday to be able to get fusion energy. Now, fusion energy would be a really great thing, because what do you burn when you burn, what kind of fuel do you use in NIF? So to first order, it's water. And we don't burn it chemically. It's not like we boil it or anything. We actually force the nuclei of deuterium and tritium together, and they burn, and they get thermonuclear burn, and you get huge amounts of energy out for hopefully very little in. And it sounds like perpetual motion, but it really isn't. And that's because you're releasing energy that's held in the nucleus. If we do this, we have a bright future ahead for all of us. This is a picture of a rainbow coming into NIF. We didn't put this in, it's just the way it was. And right at the bottom of that rainbow is that target chamber we were talking about. And that's our future. But let me tell you, I want to say something about this. This is not something that, we're going to figure out. My generation is going to figure out. We're sort of just setting the groundwork in place to prove that it's possible. But it's going to take a lot of work by a lot of young people to figure out how to make this happen. And in fact, it's going to be some of you who do it. I don't know which ones of you who do it are going to do it, but I know some of you are. When I was in 6th grade, the laser was invented. I didn't know at that time I was going to do lasers. A few days later, the whole idea of doing this ignition was thought of at the lab. They weren't thinking about me, I'll tell you that. But I know that someone in this auditorium, maybe a lot of you are going to take up the challenge of figuring out how to make this all work together. And if you do, you can have a clean source of energy for the future, for your children and for your grandchildren. So that'll be very cool. I think it'll be a great way to spend your life. So we've talked about waves. Waves are everywhere in our lives, right? Let's just talk about the things that we've talked about. What are the most common kinds of waves in your life? Does anyone want to raise their hand? Light is a common one. Sound, shock, microwaves, radio waves, sometimes, unfortunately, seismic waves. Say it again. What? Did you ever go to the hospital? What do you get? X-rays. Infrared waves, if you get a sunburn. Ultrasonic waves are another one. We didn't talk about those. So there's waves everywhere. So that's the one thing. And we learned about, they have high frequency, low frequency, long wavelengths, short wavelengths. They can be polarized. They can be transverse. They can be longitudinal. You know everything about it. You can go out there and do this on your own. So have a good day, and thanks for coming by.